All right, so welcome to I guess this is session 8. I don't know if that's correct. It's the afternoon session. We're going to talk about simulating RMG mechanisms. So we spent the morning generating RMG mechanisms, building our input file, and describing what system we want to build, and then RMG generates it and comes up with those Kempkin and Cantera files. And so next we want to talk about what we'll do with that. So first, just a little overview. Get my screen to move. There we go. About sort of the stages of, we've done mechanism construction, and now we're working on sort of the refinement side. So typically, we've seen a few diagrams of the workflow, but usually there are a few steps. You've got your model construction, and then you see what the output of it is, you analyze it, and hopefully you are able to improve some of the parameters. So as we'll see, the construction or we already saw this, the construction part is very automated by RMG. Quantum chemistry calculations can be automated to some extent. We'll see a talk about ARC. I'll also mention AutoTST, which is, I think, also kind of used by ARC, another quantum chemistry automation tool that is it's on the reaction mechanism generator organization page for GitHub. It's one of the options there as well as ARC. But one step in this process, the model analysis, can be difficult to automate. Oh, I should have mentioned at the beginning, these slides are they're Matt Johnson slides that I've edited. So again, any mistakes are me, not Matt Johnson. So lots of human hours go into the analysis, and so it's very important then to spend this time intelligently and to not waste our efforts. So some important questions we tend to ask while analyzing our model are which pathways are running, if we're doing multiple iterations, which of the model, what has changed since the last run. Always try and look at it and see if something doesn't make sense. That's a very important and understated question to ask. And trying to figure out which parameters are worth the cost of improving and will actually make the model better. So with all this said, it's very valuable to have a good tool for analyzing your mechanisms and to be able to use it effectively. This is Matt Johnson's slide. So he immediately segues into Reaction Mechanism Simulator, which is one simulator that you can use to take your mechanism and then figure out what happens when you react those species together in a reactor. So this is a Julia-based code, and it's got a bunch of different kinds of reactors in it. It's open source. It's also in the RMG organization page on GitHub, but for various reasons, mostly that I was trained in Cantera, our actual demonstration for today will be in Cantera, which I'll show you a brief comparison here. In my opinion, I do think it's a little bit easier to use, but I will say that Reaction Mechanism Simulator, or actually this is probably the best place to show it off, that it really does have some great options and can do a lot of the sensitivity analysis way faster than other simulators. And so it really is a promising avenue and worth our time exploring and learning. And there will be a session on it, I believe tomorrow, in more details. So just a quick comparison, some of the simulation software that's available that can handle the mechanisms that RMG generates. We've got Reaction Mechanism Simulator, Kempkin, and Cantera. Kempkin is commercial. Northeastern doesn't have a license for it, so that's one of the other reasons we use RMS and Cantera. We like open source software in our groups. It's good for collaboration and developing new features. The language, I will say that yes, RMS is written in Julia, Kempkin's Fortran, and Cantera is based on C++, but all of these have Python wrappers. Using for scripting, I guess I haven't used Kempkin, but apparently it's tricky to do scripting with it. On the other hand, Kempkin has a GUI, whereas Cantera and RMS do not, so it's just writing code. And then for the mechanism analysis tools, I think Matt has spent a lot of time develop these in RMS, whereas for Cantera, it's maybe it isn't necessarily shipped with a Cantera code, but people in different groups have probably at this point written a lot of different analysis software, so it's not extremely limited, but it doesn't come shipped with the software. All right, so I will talk very briefly about this. I want to keep this more of a hands-on demonstration session, but I'll just very briefly talk about what we're doing when we're running a simulation for a large model. We start off with our mole and energy balance equations. We write these differential equations based on the we can fill them out with the different species and reactions, and then we end up solving them in our solver. That's Cantera. So you can come up with a bunch of different types of reactors that you would run these simulations in. And so starting off, I'll say Matt listed out a whole bunch of the different types of reactors and their corresponding equations. You can also check. I would recommend the Cantera website has some really good documentation for its reactors about the equations behind them. I'll just very quickly highlight. So we've got our batch reactors, we've got rapid compression machine and shock tube, which you can simulate for ignition delay experiments. You can use these to compare to experiments on ignition delay times. You've got your CSTR and or continuously stirred tank reactor and jet stirred reactor, or two different but very similar kinds of reactions. These are usually steady state, and you compare those. The experiments give you species concentrations versus temperature. So that's another avenue of experiments you can look at. And then we've got a plug flow reactor. This is convenient for the catalysis mechanisms. And then you can also simulate flames in burners. So, okay, I'll talk very briefly about the solvers and tolerances and then just dig into the actual simulation code. So the choice of solvers and tolerances, so by solvers I mean differential equation solvers, can be important. And for our simple example that I'll show, it doesn't really matter, but people have spent time working on these. In general, for tolerances, if you have a smaller, as in like tighter, more rigorous tolerance, it tends to crash the mechanism or the solver more often, but sometimes you need the tolerance to be really tight in order to get the right simulation results. Let's see. So yeah, there's relative and absolute tolerances. So this describes the size of the allowable error. So for relative tolerances, that's when you, for an error, when you're taking a difference of numbers, you need it to be within a certain threshold of relative to the original number, whereas absolute tolerances are an absolute number. When you're taking errors, you need your error to be below a certain absolute value. Okay, so oh, please.
This is fine, but sometimes a tighter, more difficult to solve tolerance is actually needed to stop it crashing. So although we say lower tolerances can crash more often, if you're getting a crash, don't automatically just make the tolerance looser and looser and looser. Also try making it tighter. That might solve things.
See. Matt ran a bunch of simulations of ignition delay times. Here you can see at different absolute tolerances, and you get slightly different results. I think this plot is really informative, where it shows you can see the tolerance is getting tighter as we move to the left here, and it sort of converges at a steady value here. Whereas in this case, the tolerance doesn't have to be that tight before you converge on the consistent answer. And then he shows another one. So the difference here, we've increased the pressure, and that changes when you increase the pressure for the system. You need a tighter tolerance in order to get your system to react. Okay, and there's another convergent study where this plot is a little bit deceptive because on the one hand it is showing a convergence, but also these ignition delay times are all identical. You can see the you can't see a difference between any of the plots. But you do, I guess you do get a little bit of the numbers jumping around, but it's also important to sort of look at this and ask what it's really telling you. And there isn't a huge difference in what matters, so maybe it's not worth an extra expense in computation time if you're really not changing your final output, depending on how many simulations you have to run. Okay. Um, so I'm going to jump ahead and oh, there was one other thing. I'm pretty sure sensitivity analysis is going to be covered in tomorrow's session, but I'll just very briefly talk about it because this is one of the main things that we often use our simulator for, is conducting a sensitivity analysis. There are multiple ways to do it. I don't want to talk too much about this because I think the RMS way of doing things is much faster and better than the Cantera method that I would demonstrate, which is the brute force local sensitivity, where you basically perturb your input parameters. You know, RMG will generate a model and give you all these species thermo and reaction rates. And so the sensitivity basically says, well, what if the rate was just a tiny bit higher? How much would that affect your output concentration or ignition delay? And so you can do that for every single species and reaction in the mechanism and figure out which things are the most, which output parameters are the most sensitive to your input parameters. And then one final thing is you can pair the sensitivity with uncertainty to get to do global sampling analyses. And where is it here? So for that, you basically change the parameters within their uncertainties, and estimating uncertainties is a thing that RMG can do. It's I'm working on it currently, and we're trying to merge it back into the main branch with some updates. But at least in theory, RMG can automatically get you the uncertainties for every parameter in the model, at least as a rough estimate. And so you then perturb the parameters within those values of uncertainty and see the full range of outputs that you can get. And since sometimes it takes a really large number of samples to fully look over the uncertainty space, these are some methods that you can use to reduce the number of samples that you have to do to get representative sampling. So there's Sobel sampling, polynomial chaos expansions, which was implemented by Gao in, I believe, the 2020 uncertainty paper, which I didn't think to add here. Okay, so with that, I'm going to go ahead and switch gears, and we're now going to move on to a simulation example. I dropped the example in the chat earlier, but I'll do it again right now. Okay. So we're gonna run through this session 8 simulation with the super minimal example in Cantera. So a couple of things to start. The very first thing I would say is if you haven't run the super minimal example, you can go ahead and do that now. So I will, let's see, I'm gonna close this here. I'm back into my super minimal folder in my, this is on my Windows subsystem Linux, but if you have the Docker installed, you can go inside RMG Pi examples, RMG super minimal, and if you've forgotten, the command to run it is Python RMG Pi. Oh, sorry, this is going to be different if you're on the Docker. This is the path to my own personal rmg.py. For those in the Docker, you would it would be the same, except you'd get rid of this tilde because the root folder, the RMG is installed in the root folder. Raise your hand if you're having any difficulty running the super minimal example. and we can help you out there. I'm running it again just because I think it's good to practice running RMG if you're trying to learn how to run RMG. So here we can watch it run in live time. It's loading the databases. It printed out a copy. Okay, here it goes. It's generating, building up the model. Takes probably less than a minute. Okay, there we go. Model generation complete. Okay, so now I've got, I can look inside, oh, I'm blocking with my, hide the meeting controls. Okay, I can see inside the Kempkin folder, I've got, actually, what I really want is inside the Cantera folder, I've got this chemannotated.yaml file. So that's all set. So now in a separate window, I am going to start a Jupyter notebook. So if you're in a Docker, let's see. So if you have the Windows subsystem Linux, the command to start a Jupyter notebook, once you're assuming you're in your RMG environment, will be Jupyter notebook, and then I add this -no browser. But one thing to be careful of is wherever you start your Jupyter notebook, you'll only be able to access files inside of that folder. So I won't have access to anything that's above the super minimal folder. And so I don't actually want to start my Jupyter notebook there. I want to start it in my home folder here. Browser. So what that'll do is start a Jupyter server here, and then I can copy this link into a browser. I'll just do that example here. And there we go. And so you get this sort of GUI where you can then make a new Python 3 Jupyter notebook.
Now, the installing instructions from this morning for installing from Docker had a little note somewhere. It's like, if you want to use Jupyter, launch your Docker with some special commands that kind of maps the ports and stuff. So if you have trouble getting Jupyter to run from inside Docker and access it from outside Docker, make sure you find those instructions for launching Docker. You need to do it when you first make your Docker thing. And it's to kind of map the ports so that your web browser can access it.
Yes. So I was then going to demonstrate. So this is a different terminal. This is my Docker. I've got two versions, Windows Subsystem Linux, and then I've also got Docker installed here. So this is inside my Docker container, but I did run the command that had the special I have it here. This one, the run -it with the port here, as opposed to, yeah, this one didn't specify a port, I think is the main difference. Yeah. Okay, so anyways, if you're inside Docker, a few additions, you need the -IP to specify the port, and then also you need, in addition to the no browser, you also need allow root, because I'm the root user here, and that's I guess not a great security practice or something, where they don't want you doing that, so you gotta say, no, I really mean it. All right, so I've started my Jupyter server here, and the next step then is to open it. I'm going to go to this local host 8888. You'll notice I haven't set up the server password, so I have to enter the password. It's demanding password or token, and so I'm going to give it. Hopefully, this is the right one. Yeah, because this is root. Okay, so the token, you'll see one of these links. It's got a bunch of numbers /tree, and then token equals, and then a whole long string of numbers. And so I need that string of numbers is the password. Hopefully not with the spaces. Here we go. I copied the space there. Hopefully this will work. So I'm going to copy that into, oh, no, I definitely got the space in there. Sorry. Okay, there we go. Fingers crossed this will work. All right. Okay, so now I'm on the Docker side. Okay, so I sent everyone in the chat of the Zoom meeting, which I'm struggling to, yeah, I'm not going to open up the can of worms that is this this sidebar, but you can download this Session 8 simulation for Cantera, and you can copy it, and you can look for, you got to find that special folder where the binding is the same for Docker versus Windows. So in this case, it's my RMG files. So I'm going to go ahead and paste this example in there. And hopefully I will be able to find this now on the Docker side when I go inside RMG folders. Now there's session 8 simulation. All right. So that's sort of the sequence of steps you can take to set up a Jupyter notebook. Jupyter notebooks are great for development because they let you keep working in cells and sort of iteratively work and get feedback while you're typing your code, as opposed to running an entire script, seeing what the output is, running an entire Python script again, and so on and so forth. All right, so with that, we'll get started with the simulation demonstration. So this is using Cantera. So our first step is just to import Cantera, which we often or always abbreviate as CT, also including NumPy and Matplotlib, which are Matplotlib is really important for plotting. If you're doing any analysis with Python, you definitely want to have it. I learned this yesterday while preparing for this workshop, that a cool thing you can do with Jupyter notebooks is you can do system commands in line with this exclamation point. So for example, if I want to know the path to my Python, I can issue this command to the system. So you can do bash commands just by adding the exclamation point. So here I commented it out, but if you haven't run your super minimal yet, you could potentially run it by commenting that out and doing the system command inline in your Jupyter notebook, which I thought was cool. And even you can develop for many years and you'd still find new things all the time. So that's pretty cool. Okay. So moving on, this block is the command for, I'd mentioned earlier, if your RMG run crashes before you get to the end, maybe this happens to me frequently when I'm running long combustion models. It'll generate something with hundreds of species, and I just run out of I hit the time limit for the compute node that I'm running on. And so it's built a really big model and potentially a good model, but it's still it didn't have a Cantera file. And so then you'll have to do the ck to YAML command. And so this block, all it's doing is collecting the different pieces that you need to run that command. So you need the path to the Kempkin file, you need the path to the transport file, and then you can specify the output file. And since I am on the Docker side, my RMG path will be here. So the command I would run to convert the ck to YAML is then here. I can copy that in to the next cell and run that. That did not work. Let's see. Oh, that's because I didn't run the super minimal on this side of the Docker, which is fine. I can just run it here. All right, so that's going to take a minute, so we can keep moving on while that runs. So, all right, so the first step, if you want to simulate a file that you generated from RMG, is to load that RMG, or the Cantera YAML file that RMG outputted. So I do actually need that Kempkin file, which it's in the process of generating. One alternative I'll mention, Cantera has some inbuilt mechanisms that just come with Cantera the package. So the GRI 3.0 mech is useful for if you want to just like test out Cantera code on something. It can be very helpful to just use one of the built-in packages. The one thing you have to watch out for, if you need accurate chemistry, don't use this. It's like 30 years out of date, and you want to use the nice mechanisms that you spent all that effort generating with RMG. So let's see if that is done running. Okay, it looks like, well, we'll see. It looks like that worked, or it did run. Okay, so my super minimal is done running on the Docker side, and so I have loaded the mechanism with this CT solution command. So what that does is it loads everything that's in that that long Kempkin or Cantera file, all the species thermodynamics and reaction rates, and puts them in this gas object. And so you can get a little bit of the details of the gas object just by, oh, this has been small the whole time. Let me see if I can zoom in a bit. It's not much better, but okay, so the gas has a temperature and a pressure, and you can see some of the properties, and it doesn't really tell you the species because I haven't looked into that yet. So this block here will tell you exactly what species and reactions are in your mechanism. And so you can see here are the 13 species. It's really just an O2 plus H2 reacting together. And here are the reactions. Usually there are too many reactions for you to want to just list them out. That's often not helpful in the way that just looking at the species might be. Oh, one other thing to mention about the species, you'll see there are all these numbers after. So this is RMG is attaching the numbers just to make the species label unique. And so sometimes if you want to reuse these Jupyter notebooks, if you hard code the species label, you might have to change the numbers. And so that's why I recommended earlier, if you're going to rerun RMG a bunch of times, it's helpful to put the species directly into the input file so the name will always be the same. Okay, so we've got species and reactions loaded from an RMG run. So now we're going to set some simulation inputs because we want to simulate this inside a reactor. So we'll set a temperature, pressure. So temperature is 1,000 Kelvin, pressure 1 atmosphere, but this is specified in pascals. And then our starting concentration will be mostly hydrogen and then a third oxygen. And we're going to simulate this for 1 second. All right, so then setting up the reactor, we're going to use a very simple batch reactor. So we start by setting the temperature, pressure, and mole fractions for the gas. So those are just the values I had defined above. And then, yeah, there's our T initial, P initial. So the next thing you do is you make a reactor object. In this case, I've used Cantera's ideal gas reactor. You can go ahead and I would recommend checking out the documentation for Cantera. Just to note, this is the version 2.6. If you are using a more recent version of Cantera, this is the version that ships with RMG. So if you're just using your RMG environment, you don't have to worry about changing the changing this particular link, but the documentation has been updated with the newer version of Cantera. So you can see what the ideal gas reactor is expecting. It wants some sort of contents. It wants to know what kind of gas is in there. You can name it, and then you can tell it whether or not to solve the energy equations. So we're just going to start really simply. We're going to put the gas inside the reactor, and then we're going to define a simulator, which is a network of different reactors. So I'm going to run this block, and I'm going to run the block above it, which I forgot to. If you want to restart the reactor for later simulations, you'll have to rerun this block right here, setting the gas in reactor. Okay, so next up, we're going to run the simulation. So there's a couple of different ways to keep track of your variables as we step through it. So one way is you can make lists. That's sort of a native Python way of keeping track of things if you don't know how long the array is going to be. A sort of more elegant way to do it is using the solution array object in Cantera. And so that basically saves a snapshot of the gas at every single time step. And then you can specify extra parameters. The reactor time is not automatically saved in the gas object, and so I've added that on as an extra option. So now we're ready to go in and run the simulation. We use a very simple while loop. So while your simulation time is less than, we specified this would be 1 second, we're going to save the state of the gas, and these lines are using the list that I had defined, and then the solution array is getting added on here. And then we're just going to do sim.step. So that's telling the solver to go one tiny step. It determines how or what time length is appropriate. So when it starts off the simulation, it does really, really time evolutions. And then once, as the chemistry changes, it tends to take larger time steps. So this runs very quickly. And we've run our simulation. So now we want to plot the results. So remember, this was hydrogen and oxygen reacting. So when it reacts, the temperature increases at about 0.4 seconds. We can also plot the pressure. So the code here, the difference I was going to show between here. So in this case, I'm plotting 2 lists. So I'll just, we can interrogate these here. You can see the times. It's a list. And then the temperatures, is that, I named it T's, that's why. Temperatures are these values, and so for our plots, we just do times versus temperatures. That gets us that plot, and then for pressure, very similar, but this time I'm using the solution array. So the solution array object was time history, so time history.time, and time history.pressure. And so there's the results of our simulation. All right, so next we're going to do species concentrations. And so I've added a tolerance threshold where it has to reach at least 0.001 of the mole fraction in order to be plotted. So that's what this is. It's checking if at some point, so if the maximum, this X here is the concentration. I've sort of made this very compact. So time history X is a big matrix. It's 3,000 time steps by 13 species. And so if I want to get, for example, the whatever our first species is, all of the time steps. So if I wanted to do just a single time step, I could do the time versus, I think this is argon in the model, so it should just be a straight line. Yeah, not particularly interesting, but if we pick, I think like oxygen or hydrogen might be like, I'm gonna guess 6th. Yeah, this species is reacting. So anyways, we can put those all together then, and we can plot all of the species that at some point are at least 0.001 of the overall mole fraction, or the overall composition. And so we can take a look here. We've got our legend. You can see it starts with mostly hydrogen. It all reacts down, or not all of it, but a lot of it reacts away. Our molecular oxygen also mostly reacts away, and it forms I think that's water. Yeah. Yeah. Yeah, be careful. It's a trap. Okay, so that's a basic simulation of the concentrations. I'm sorry I'm rushing. I'm already over time, I realize, but I also have the next session, so I'll just take away a little bit from the tools part. So are there any questions so far on plotting what we've seen, concentrations or temperature or pressure as a species evolves or reaction evolves in a batch reactor? So that's just summarizing what we've done so far, is simulate hydrogen and oxygen reacting in a batch reactor.
So I would need to type in all the commands which you have prepared, probably the plot commands and so on. I need to type it in the Jupyter, or is it predefined in my output file and I can simply run it in Jupyter?
I'm sorry, I don't think I understood the.
Okay, so you have many plot profiles in your Jupyter browser workflow. Do I need to, if I have run a RMG simulation, do I have to type in all the plot commands, or was that included in my RMG solution foil?
The plots, you can turn on the species plots, or you can turn on a version of species plots. So you can get the RMG's very simple batch reactor. You can, I think there is one of the tools I think does that for you. So usually, I would say in my experience, usually for most applications, you want to write your own Cantera simulation code, if only because the conditions that you want to simulate at are specific, whereas for RMG you typically specify like a range because you want to give it a little bit more leeway, I think.
Yep, sounds fun.
So you would write this code, but you don't need to rewrite it every time, right? Once you've got this notebook, you can run the notebook again. And so she's showing like how you do it from scratch, but
Yeah.
she doesn't do it from scratch. She uses the one she did last week.
Yeah. Yeah.
Last year or 2 years ago or whatever.
I was gonna say more accurately, I used the one that Emily did 4 years ago. Yeah. So this is yeah. Also, once you run the simulation for these plots, the answer for or the state is saved in the solution array, and so you can come up with a lot of plots without having to rerun the simulation, because often the simulation takes a lot of compute time. Okay, so I'll just add, I think I had a small example about ignition delay and rate of progress. So a few other things that are saved in the, I say the state, this gas object keeps track of what's happening in the gas. And so you can use the tab autocomplete to help see what your options are, like what sort of things are saved in the gas. So you can see it's got things like atomic weights, activity coefficients. I'm going to scroll down to, it's got forward rates of progress, and it's got a lot of things. I would say you probably need a full Cantera tutorial to get the full suite of things in here, but I just wanted to scroll down to show the net rates of progress. Here we are. So this is also an array. So this is there are 19 of these because there are 19 reactions. So these are the overall rates for every single reaction. This is at the final time step, this value of gas. And so we can see which reactions are overall producing the most, which reactions are going the most. And so for this block, I decided I only want to plot the top 10. I'm actually going to reduce that to, or actually no, I'm not going to change it because this is the one that I practiced with. So this is a little bit of, it's a little bit tricky where we're doing some sorting here of a two-dimensional matrix. So we start off with net rates of progress is saved here. So once again, I'll show you the shape of this array is a 3,000 or it's like 4,000 time steps by 19 reactions. And so what I'm doing with this line is figuring out which reactions have the highest maximum value, or just getting the maximum value for every single reaction. So once I run this, I'll have 19 maximum rates of progress. So then these two lines are going to sort. I'm going to sort the, this is just a indices counting just numbers from 1 to 19. And so I'm going to get a sorted order of those according to which has the highest rate of progress. And then I'm going to plot the ones that have the, that go in that sorted order. So it might be better to just run it. So what you can see is that the rates of progress, this is on a linear scale. So pretty much nothing happens until it ignites, and then everything happens. And so this is maybe not the most useful time or rate of progress scale to look at things on. And so I'm going to change the scale to a log scale so that we can separate out these reactions and see that starting off, actually the most important or active reaction here is hydrogen reacting with OH to form water and hydrogen radical. So these first two are happening a whole lot, and then pretty much everything falls off toward the end. So the point here is that plots like this that show you the rate of progress can help you show exactly which reactions matter. And also it's important to consider which reactions matter at which times, because sometimes at different times, different chemistries will dominate. And so you need to know which time scale you're interested in. All right, one last demonstration here is with ignition delay calculation. So ignition delay, if this were a shock tube or rapid compression machine, it would be the time from the initial spark until everything ignites. And that's usually defined either as the time at the highest change in pressure, or it's often measured with photosensors that look at like OH or CH radicals, I believe. And so if we wanted to calculate the ignition delay time, we can do that with NumPy by, we can use the gradient of pressure and then find the time at which that's the highest. So here our delay time is 0.44 seconds, which matches the plot here. Everything happens at 0.44 seconds. So one last bit here, we can redo the tolerance experiment that Matt had done in his slides, where we basically, before we get there, you can plot a vertical line at the exact delay time to see if we got it. And yeah, you can see the pressure, it gets the delay time. I'm gonna zoom out a little bit to see the full plot at exactly the time of maximum pressure rise. So one thing to mention here, it's always good to look at your plots and make sure that they're telling you what you think that they're telling you, rather than just trusting a random number that you get out of a simulation. So what we can do with our ignition delay experiment is we can change the RTOL value from 10 to the negative 15th to 10 to the negative 3rd, and then simulate the ignition delay time at every single, I always forget to run the ignition delay times for every single tolerance. So what you'll notice at first is that when you have a really tight tolerance, it takes longer to run. And then we'll see gradually as the tolerance decreases, the simulation gets faster and faster and faster. And then we can plot the ignition delay time versus the relative tolerance. And you can see kind of like Matt's plots, at some point when your relative tolerance is low enough, it sort of converges on a final answer.